Hello, everyone. Welcome to today's lecture. And today we are going to wrap up the discussion about the performance, and then we are going to spend the main bulk of the lecture on file systems. And so let me start. So just a recap from last week. Last week we talked a little bit about performance. And this is one way to model the performance, in particular for something like a network. And we are talking then that, for instance, if you send a packet with a certain number of bits, say small b, and the network capacity is capital B bits per second, then this is a formula for latency. You have a factor S, which is overhead to send that packet, for instance, of the system call, and then plus a variable part, which is B is the number of bits in the packet over the capacity of the link, capital B. This formula also works reasonably well for transferring data from the disk. In this case, the S, it's represent the rotation latency plus seek time. So this is one, and this is a formula for the latency, and you see here is shown on this plot with a blue line. So the intercept of the blue line with the y-axis represents the S. So in this case, it's 1,000 microseconds. And then here, the slope represents the bandwidth of the particular link. So in this particular case, we are going to have a link of 100 gigabits per second. S was 1,000 microseconds or 1 milliseconds. And then B is here on the y-axis. Okay, so on B it's 5,000 bits, then you are going to get the corresponding 5,000 over I think that should be bytes. It's 5,000. It's 5,000. 500,000 divided by 125 megabytes per second. That will give you 4,000 microseconds or 4 milliseconds. And if you add to S, which is 1 millisecond, you are going to get 5 milliseconds or 5,000 microseconds. Okay, and then the other important metrics here is the effective bandwidth, which is basically, okay, if I'm sending a packet of this length, what is the effective bandwidth for that, sending that packet? And that obviously is a packet size, in this case, B, over the time it takes to send the packet, which it does include S, the fixed overhead, and this is a formula, B, capital B over capital B times S over B, small b plus 1. Okay. You notice that if S is 0, then the effective bandwidth is equal with capital B, which is expected, right? Because there is no fixed overhead, then the effective bandwidth, you can send data as fast as the capacity of the link. And one important metric here is about it's a half power bandwidth. And half power bandwidth is a way to think about it. It's basically what is the size of the packet in this case I need to send such that the effective bandwidth to be half of the capacity of the link, right? So the overhead is not that very high. Overhead, it just cuts my capacity to half, right? And here with red, you can see the curve. This curve with red is the effective bandwidth, again, versus the capacity of the link. And when the number of bits, is 0, obviously here you have effective bandwidth. It's 0. Okay. And on this plot here on the right, this is a plot which has two y-axes. On the left-hand side is the latency, the blue one, the blue curve, the blue line, and on the right-hand side, you are going to have the bandwidth, effective bandwidth, which is the red line. Any questions? So next, remember that we also did a little bit of queuing theory, mostly providing you some formulas. So just summarize them here. And as you know, this is topic, it's covered. This is part of the exam, the midterm topics, and so you may get a problem which is about queuing theory or about performance, higher performance. So anyway, so here you remember that this is a queuing model. Obviously, it's called a queuing model. So for a reason, it has a queue. So you have a bunch of requests here with the arrival rate lambda. Lambda is the number of requests, average number of requests per second arriving to the queue. And the requests are removed from the queue as fast as they can be processed by a server. And the server processes each request at the service rate mu. And mu is O1 over the service time. How long it takes to service a particular request. So the way to think about, if the server takes 100 milliseconds to serve a request, then obviously mu it's 1 second over 100 milliseconds is 10, because you can serve 10 requests per second. Okay. So then another important parameter is square coefficient of variance to characterize the systems, and the server utilization. The server utilization is basically the average arrival rate over the average service rate. And fundamentally, you do want these parameters to be less than 1, because this would mean that the system is in the stable regime, and in a stable regime, if the arrival rate is lower than the service capacity, about how fast the request can be served. If you send more, obviously the system will not be in a stable regime, which means that the queries, the queue will grow indefinitely, right? As more requests comes in, and the system cannot keep up with serving these requests. Okay, and all the results typically in the queuing theory assume that rho is less than 1. And then the parameters you want to compute is the time you spend in the queue, right? We know how long it takes a request to be served, so it's t serve. So now we need to understand how long it takes a request to is going to spend in the queue. So then by adding the two, we know the service time for the queuing time. We know how much a request spent in the entire system, which is what matters from the user perspective. And then we also want to, we learn about the little law, and the little law allows you to compute the queue length by just multiplying the mean arrival rate plus times the spending, the time times the average time spent in the queue. And this are some of the results we went over last time. So it's again, this is a recap, which may help you for the tomorrow's midterm. And TQ is for MM1Q, which is, remember, an MM1Q, it's one of the simplest queues out there. It has means that it has one server. The first M refers to the distribution of the arrival rate. So this means that the intervals between two consecutive requests arriving is exponentially distributed, or it's also called Poisson distribution of the arrival rate. And also the service time is exponentially distributed. It's again, the time it takes to serve, it's exponentially distributed. And the formula here is T serve times rho over 1 minus rho. And for a more general queue where the serving time, it's general, it's just characterized by this C, we know only about the square coefficient of variance. You have a very similar formula, only the second parameters in the formula is different. But the real main point to notice about this formula are this last term, which is rho over 1 minus rho. And this capture what I said earlier, that if rho should be less than 1, that if it's equal or greater than 1, then the system will not be in a stable region, right? And this is a plot showing you roughly how the response time and the service time is looking versus the throughput or utilization versus rho. So on the x-axis is basically rho is from 0, say, to 1, and this is the response time. The response time is the queuing time plus the service time. And as the rho goes to 1, this is going to be dominated by the queuing time, because the queuing time is going to grow when rho it's close to 1, then this goes to infinity. Okay. So any questions? Okay, so now let's talk about how we are going to optimize the performance and what are the ways to optimize it. And this is what we are going to discuss over the next several slides. And again, if you look about for an IO device, you are going to have the user thread. This is where the program is running. Then you are going to send requests, say read or write from this particular file, which is from that one particular device. And these requests are queued and then are submitted to a controller, and the controller is going to program the IO device to read and write the particular data. Okay, and so how you are going to improve this system? Well, there are a few ways. One, speed, right? You can make everything faster. Each of these components, you can make it faster. You reduce the overhead of the context switching. You have also some context switching here of the controller and of the device, right? You buy a disk which rotates faster with a lower seek time. Another way is parallelism. It's basically, you can parallelize. You can have, inside, you can have multiple queues if the queue observation are expensive. Or instead of an IO device, you may have multiple IO devices. You can, for instance, as you know, probably you can have 2 disks, and then you are going to stripe the data across disks. So therefore, or you just partition the data between disks. So when different requests can run at the same time on if they are going to request data on different disks. Then is overlap, right? So this applies to different parts of this kind of pipeline. So for instance, for the thread, you send a request, you are waiting for the request. You can do some useful work instead of just waiting. The same thing here is like for the controller, as you program the current request and you program the IO device to satisfy the current request. Once you do that and you send the request to IO device, then you can process the next request. The one important aspect here that one way you to look at this pipeline, say you want to improve the performance here, what you are going to do, the engineering way to look about, or software engineering way, the sound way to do it is to look where the bottlenecks are, which is a bottleneck, which is the slowest part in this chain. And then you are going to focus on that bottleneck part to improve the performance. Because if you improve the performance of something which is already fast, not the slowest link in the chain, then the end-to-end performance will not improve much. Okay. And remember, the queues are here to absorb the burst. The queues is that because the requests are not going where, are equally distanced in time. They can arrive, a bunch of requests at the same time. So the controller cannot serve all this bunch of requests at the same time. So you need to then queue them, because if you don't have a queue, you need to drop on the floor this request. You need to, you are going to fail satisfying this request. And finally, another things we didn't discuss last time, it is one other techniques in this kind of systems, it's admission control. The admission control basically says, look, and in admission control, why you have admission control in general is that you basically admission control says that I'm telling you this request I cannot handle. Okay, so the thread wants to submit a request, and I'm saying, the controller or the queue itself saying, I can no longer enqueue this request. Come later, right? And this also typically happens if we want to ensure to provide guarantees in terms of the end-to-end latency, of end-to-end response time. Okay, in order to provide, so basically saying, if I'm going to accept a request, I'm going to guarantee that I'm going to serve this request in, say, 100 milliseconds, right? If I cannot, if there is no admission control, then I cannot make that guarantee, because if there are a lot of requests coming, which exceeds the capacity of my system, I cannot guarantee that each request is going to be processed within 100 milliseconds. Okay, so admission control is hand in hand with limiting the delay if you want to have guarantees on the end-to-end delay. Any questions? Can you give an example from real life where the admission control is employed? Any example? Okay. Yes, red lights on the entrance of the highway. That's a great example. And real-time systems, yes, although I wouldn't call it real-time light. Red lights on the entrance of the highway. That's a great example. And there are many other examples. Like for instance, during when there were more restriction during COVID, during the pandemics, some shops, you limit the number of customers who are inside. So in order to make sure that they can keep distance among themselves. There are even more obvious examples. Like when you fly on a plane, it's admission control, it's your seat, right? You cannot, it's not like in a bus in which there is no admission control, anyone can get in. Well, I guess it's a natural one. People will no longer fit in a bus, and it's that's a natural pushback mechanism. But yeah, there are many examples in real life where you are having this, so to speak, admission control. Berkeley course waitlist. That's a great one. Yes, Richard, that's great. Okay, thank you. So when is this performance highest? Remember, obviously, when there are sequential reads, and this is subtle, and we are going to see this is for the next few slides. There is another when there is so much work, you get so many requests, you can piggyback. You can have so many requests, but can reorder the request says that you can serve this request much more effectively. We'll see that in a bit. Now, if the system is mostly idle, it's perfectly fine to be inefficient. No one cares, right? And burst, this is an important point, right? When you have a burst, meaning that you get more requests than the system can handle, so you need to queue those. It's both a threat, or should be threat there, because they can increase the latency, right? Because you queue this request. But it's also an opportunity because you can do this piggybacking. You can, again, reorder the request, as you'll see in a few slides, or you can do batching. Batching meanings you can, for instance, you have many requests, you can do one context switching or function calls. You can think about, you can do one context switching to handle multiple of these requests at the same time. So you amortize the context switching across multiple requests. You can also waste the space for speed. Like for instance, you can, you know, when you write on the disk, like let's see, what will be a good examples. Yeah, you can have for instance, like for instance for page tables. For page tables, you can have additional hash maps, which you are going to keep in order to locate, to map the pages, the virtual pages to the page numbers, to the physical page numbers. Another way to do it is to increase the size of the TLB. Another way to increase the performance in what you learn we learned in the past is to increase the cache size. In order to also improve the performance, system performance, program performance, you can also increase the memory size. Of course, there is a Baladi anomaly, which, as you know, for certain page replacement policies, increasing the size of the memory, of the size of the cache, doesn't necessarily reduce the number of faults, page faults. But in general, for many of the page replacement policy, like LRU, that's you know, increasing the memory size always doesn't, you know, will likely decrease, most likely will decrease the number of page faults. These are a few examples where you can have increase the space to increase the space and to improve the speed. And other techniques are reduce the overheads through user level drivers. So basically, if you can implement the functionality at the user level, you may avoid the context switching because you don't need the operating system in order to handle these requests. And the other one is, like I mentioned earlier, the overlap. So while you are waiting for an IO to complete, you are doing the more useful work. And this can happen at multiple levels. It can happen in your the operating system. As you know, when operating system on a thread is blocked on an IO device, on an IO request, is going to switch it out, putting the thread on the waiting queue, and is going to schedule, the operating system is going to schedule a new thread, which is on the ready queue. Okay, so now we are going to look into a bit into the disk scheduling, right? The disk, remember, is quite complicated, right? It has multiple plates, and each plate has two surfaces, up, down. And then you have cylinders and sectors, right? So when a request comes in from the operating system to read or write on the disk, it's going to tell you, typically it's telling you what is a cylinder, the face, the surface, and what is a sector, right? Here we are considering a simpler example where you have just the cylinder and the sector. And this is how the request look like. So in this case, you have two numbers for each request, the cylinder and the sector. The request also is going to specify what is the read and write. And because this disk is slow, more likely you are going to have some requests which are queued. Okay. So now the interesting aspect here, the requests are in general independent. So now the question is how you are going to serve these requests. The simplest way is FIFO, right? You serve the request in the order in which they arrived. This is fair among the requester, it is fair with respect to the order in which they submit the request. But it can be very long six. Why? Because the head can go, randomly from, from one cylinder or one track to another, right? You don't want that because you remember the seek time is very expensive, right? As well as, rotation latency. So you don't want to go, you want to be smarter than that. So what will be a smart way to do it, right? If you want to minimize the seek time, once you serve a request and you are in a certain position on the disk, you want to look in the queue and take the request which is closest to you, because if the request is closest to you, you are going to minimize the seek time. And this is shortest seek time first, right? You pick the request that is closest to the head on the disk. Okay. Of course, in general, you also need to include the rotation late delay, not only the seek time, but for now, let's simplify it only to seek time. Okay. So now the seek will reduce the time, if you look, but it's not good. What is not good is that may lead to starvation. Like for instance, if a lot of requests come and they are clustered close by, then according to these disciplines, you are shortest seek time first, you are going to serve this request. And the request which is farther along, which is farther, like for instance, at the edge on the edge of the disk, may wait for a long time to be serviced. Make sense? So you don't want that. So again, great average seek time, but it's unfair. Can cause starvation. So one solution to that is scan. It's a pretty nice solution. These are what you see here, these numbers. Think about these are tracks or cylinders. Right? A cylinder, it's all the tracks which are under the heads on different platters. So scan is basically you start going into one direction, either to the edge of the disk or to the inside of the disk. And you are only going to serve the request in the direction you are going, right? So you serve the request on, say, track 53. Then you look in the queue and you have multiple requests. Say you pick the one which is closest to you in the direction you are going is 37. Then the next one is 14 and so forth. And in this time, so for instance, if when you serve the request 53, you get the request 65, this is closest to you. So according to the shortest seek time first, you serve this request. Because it's not in the request on track 65 is not in the direction of your movement. You are going to ignore it. Right? So you go until the last request in your direction, and then after you reverse. So here I say no starvation, but still retain a flavor of shortest seek time first. Why is that? Tell me, why is that? Why do we still have a problem with this one, with scan? By the way, it's also it's called elevator algorithm. Can you think about, does scan exhibit any unfairness? And why, if yes? Yes, Alison, so say you may never reverse if tasks keep arriving at the same spot, so basically on the same track. That's true. That's a pretty edge case. It's a good answer, but it's a little bit edge. What else? Can you think about some other requests which will get preferential treatment if they are in some region of the disk versus others? Oh, Carl asked a question. How do we define the initial direction for scan? I guess, I mean, it's a good question. I think, I don't know, but I don't think it matters. You can choose anyone initially. Yeah, there is more data on the outer rings, so traveling it's disfavored. Yeah, you are right. It's like, let me see, it's also a question here. Okay, it's the same question. So Carl, it's again the answer to your question, how you define the initial directions. I think it doesn't matter. You can but I do not know, and I don't see a reason that's very important. And going back now, it is going back about when this scan is not fair. So here one is not fair. Which requests are for which requests does scan provide advantage, favor them? So here, the request in the middle, you get quicker to the request in the middle, right? Like for instance, I can go to a request, say it takes, 1 milliseconds to go from one end to another end, right? If I missed a request arrives here, just after the scan has passed in that direction, just I missed it. So I say, okay, it goes 0.5 milliseconds to one end, and I wait for another 0.5 milliseconds to come to me back. So I wait for 1 milliseconds. But if this happens when I'm at the edge, so I just missed the head, which now goes towards the inside of the disk, then you have to wait for 2 milliseconds. Need to wait 1 milliseconds to go all the way to the inside and 1 milliseconds to go back. Again, I'm oversimplifying things here, but just to give you a sense. So scan favors the requests which are in the middle, right? And not the requests which are at the edges. What is the solution here? Well, the solution is circular scan or C-scan. And this basically just go one direction. So say you go always to the, you serve the request only in one direction. And when you are done with those, you immediately go to all the other edge and start serving them again. Okay? So that's kind of what it is. Right? So if a request, I just misses the head, no matter what the request is, on the average is going to wait for the same time for the head to come to be back to be served. This is not biased towards the pages in the middle. Finally, I mentioned you can hide the latency. How do you hide the I/O latency? If the blocking interface is await, we already discussed, you have a block read and write system call, you put process, the operating system put processes to sleep until the data is ready, the request is served. And during this time, the operating system schedules tasks, ready tasks, which can use the CPU. Non-blocking interfaces don't wait. So basically this, you remember, this is an interface in which you are just going to issue the request, but then returns immediately. You just, after you return, you do something else, right? And then later you need to go and see whether you got the data. Okay. Or you wrote the data to the kernel. And asynchronous interface is tell me later. Again, it's like in the non-blocking interface, it returns immediately the request, because in this case, for instance, when you catch the data, you allocate the buffer, you give the pointer of the buffer, and tell the operating system basically put the data when available, starting from this pointer, right, in the buffer. Okay, and then let me know. And when you send the data, is the same, right? You are going to create a buffer. You are going there. You are going to want to, you know, you are where you put the data where you want to send, and then you give to the kernel, to the OS, in the right operation, in the right system call, you give the pointer of the buffer you want to be transferred. Okay. So now recall the entire hierarchy for the I/O. This is a top part which provides the API and the abstraction to the applications, whether it's streams or it's a block API plus the system calls open, read, write, and close. Then at the bottom, we also covered last time, this is about I/O drivers, controllers, right? These are the drivers which are interacting with the physical device, read and write the data to the physical device. And the middle is a system which kind of makes the conversion in some sense from the API, which is provided to the application by the operating system, and the API of the I/O driver, which is a block interface in general, right? So more precisely, for the API, for the higher level, for the application, you typically have a variable size buffer. And for the file system, which you are going to talk more about this, you are going to have blocks, but the blocks are logically indexed. These are where the data is stored, right? Logically indexed means that the index in the operating system is not the same index which of that block on the physical device. This is done by the hardware device and by their controllers, mapping from this block device from the operating system to the blocks or the sectors on the hard disk drives. Remember that the blocks in the operating system are typically have like 4 kilobytes. And sectors on the hard disk drives are smaller. They are 512 bytes. So you have typically, you can have 8 sectors for each, or a block requires 8 sectors. And you have an SSD, you remember you have these flash translation layers, which again maps the logical index of the blocks to the physical blocks. That's pretty much what you have. And also you have erasure pages. So Let's look now, we are going to start looking a little bit more depth to the file system. And one way to define it, like I mentioned, it's a layer of the operating system that maps the API provided to the application, which is files, directories, a stream of bytes, into lower level API of the IO devices, which is a block interface, right? And there are a few things, this needs to be done, the operating system. And that's naming. You need to find file by name. You don't give to the OS a block where the data is. You let operating system worry about mapping between the file name and the block. And this is part of the organization. Also part of the organization is about the file names are typically within directories. So you need also to locate the file name within a particular directory. Also need to provide protection. You enforce access restriction. When do you do that? When you open the file typically. And also finally, reliability. Why do you store the data on the disk? Because it's durable. You want to survive, data to survive when there are crashes or when your laptop is powered down. So from the user perspective, then I have some data structures which I want to store those data structure durably. That's what I want as a user. And that was a file system should offer me. Now, from the system view, and I'm talking here about the call interface, the API as a boundary of the boundary between the operating system and the user space. The system sees what it doesn't have any idea about what data structure the application has. It just see a bunch of bytes, a collection of bytes. So the system then needs to take this collection of bytes, this bunch of bytes, and write them on this device, on the device hard disk drive. Then the system view that it's inside the kernel. This is the one which interfaces to the devices. It takes a collection of block and it sees a collection of, instead of takes a collection of bytes and maps them to a collection of blocks. The collection of blocks, they are still logically identified. Logically, again, means that their identification is not the physical identification or those blocks are on the disk. Okay. And like I mentioned, the block size is typically greater than sector size. So let's see what happens when, for instance, the user says to the operating system, I want bytes between 2 and 12 from this file. Well, the operating system has to fetch the block corresponding to those bytes and just return the correct portion to the operating system, to the application. What about when you write bytes between 2 and 12? You fetch the block from the disk, you modify the relevant portion, and you write down the block, back the block. So you take, for writing these 10 bytes, you get the block, which is 4 kilobytes, update these 10 bytes, and then write back the 4 kilobytes. Okay. So everything between the operating system and the devices is a block granularity. So therefore, if you you always are going to pay the overhead of reading and writing blocks as a block granularity. Okay, so let's it's again a file system. You have directories and files. Directory, you can think about that the user visible index, mapping names to files, and the disk is just a linear array of sectors. You can look, right? It's a sectors on, you have a bunch of sectors on a track, and you have a bunch of tracks on a face of a platter. And then for each platter, you have two faces. And then for a hard disk drive, you have multiple platters. Right. So therefore, a sector is defined by, like I mentioned earlier on, by the cylinder, the surface, and the sector. Okay. Now, the main point to take from this slide, and it's re-emphasizing what I said earlier on, is that in the operating system doesn't track at the level the sector using their physical identifier. The physical identifier again here is the cylinder, surface, and sector on the disk. Instead, you have a logical block addressing, and typically now the controller translates this logical block addressing to the physical block addressing. It's something similar with virtual addresses. The way that the operating system is responsible for translating the virtual addresses to the physical addresses. Okay, it's a good. Let me answer this question from Allison. Why don't we build devices that let us do lower, basically, I guess, lower granularity of reads and writes? I guess, this is a very good question. And the answer is the overhead. So you are correct, Allison. This is because efficiency. Remember again, just think about the hard disk drives. If you remember the hard disk drives, in the last lecture, there is some example. The seek and rotation latency were like 8-9 milliseconds. And the time to transfer a block, even if the block as a sector, even if the sector is 512 bytes, it's not only 1 byte, was much less than 1 millisecond. So the time to transfer, to randomly access and transfer a sector is dwarfed by the rotation latency, by the fixed overhead, rotation latency and seek time. Okay. So is it because there is always an overhead? Another way to think about is, here it is another way to think about, and maybe let me just, and to connect the dots here. Remember this slide? Look here at this formula. Okay. The smaller the bees, the less the effective bandwidth is. Right? If B is very small, S will dominate the fixed overhead. This is just overhead. It's useless work. And the smaller the B is, the lower the effective bandwidth is. Look at the red curve here. Okay. So that's what you have. Each request, processing each request has a fixed overhead, even if it's on, even if this is on, let me go here, even if this device is solid, it's SSD, not disk drive. There is an overhead for controller, is there an overhead for context switching and things like that. Okay, hopefully I answer your question. Okay, let's go back. So what do you need for file system needs? What, you know, if you design a file system, what do you need to be careful about? And you need basically to track which, for a file, which are the blocks containing the data from that file. You need to track it. You need to, for a particular file, you need to know which directory contains it. And then you need to track the free disk blocks, because if you write something new in a file, you need to know which blocks are free, are empty. And then you also need to decide where to maintain this information. And the answer is the information has to be persistent. So because it's persistent, you have to maintain it on the disk. So it's again, data structures on the disk is different from the data structure in memory. The application, you have a data structure. The disk or even the operating system is unaware, completely oblivious about the data structure you have in your program. It just sees a bunch of bytes and later a bunch of blocks. That's what it is. Again, because you access a block at a time, is not very, these things, accesses are not very efficient for when you access just a byte. And obviously, like I mentioned, when you write to a disk, you expect to be durable. That's why you write to a disk. Otherwise, you keep the things in memory. But here you need to be careful. You cannot assume that if you write to a disk, if you say I call a write operation, everything is fine. Why is that? Tell me why, if I just call the write operation to a file, I cannot be completely sure that the data I wrote has been stored durably on the disk. Yes. If you remember, we discussed early on about buffer cache. So the data is not stored directly on the disk, it's stored in a buffer, right? So if after you submit the request, the application fails, the operating system fails, the data may be lost, right? You need to call, what do you need to call in order to make sure that the data goes to the disk? What system call you are going to invoke? Flush. Very good. Although I would wish also to have more people answering these questions. So it's again, it's not a wrong answer. It's about discussing it, and you'll remember much easier if we have this kind of discussions rather than me just talking and talking and talking and being boring. Okay. So, okay. A few announcements, you know very well. Tomorrow, this is 11/3. Let me just make. Tomorrow we have the exam. I wish you the best of luck. All the materials is up to and included the last lecture, not this lecture. And the project deadline, it was pushed. So now you have a little bit more time. So hopefully this really helps you. Okay. Again, let's go even deeper talking about the file system. So again, a few core elements. The file system design, if you are talking about the performance, the dominant factor. Remember, you are talking about this bottleneck. The bottleneck is a disk performance. The disk works better, provides the best performance when we sequentially read and write data because we avoid seek times and rotation latencies. So you want to maximize these operations. Remember, it's a file systems abstraction provided in Unix. You need to, it's open, close, and in between you read, write. You cannot read and write to a disk without, or to a file system, to a file, without opening and closing that file. The cool thing about this is that you can perform the protection checks, admission control, and all at the open when you open the file. Otherwise, you would have to check for protection every time you access that file. The size of the file is variable. When you start writing, you start with one block. You need more than on one sector. You need more, the file system is going to allocate more. So you don't need to predefine. This is very important. You take it as a given. But it's not. Another design is like you would just allocate space on the disk and before you start writing. Right? And why is that natural? It can be natural because how do you do it in your favorite programming language like C, right? How do you manipulate the memory? How do you manipulate the storage in memory? You know, before you read or before you write some data, what do you need to do? You need to allocate memory, malloc or calloc. So you allocate first and then write. Here is not needed. You just write, and the operating system and the file system in particular will take care of growing the size of the file as needed. The files are organized in directory. You have a directory structured, and this directory structure, the directories is and file. It's also stored on the disk, and then you need to allocate. When you allocate file, I think we are going to see that in the next lecture. When you allocate more sectors on the disk, you want to allocate them contiguously. Why is that? Because when you read the data, if this data was written on a bunch of sectors which is contiguous, you maximize the sequential writes, sequential accesses, right? Sequential reads in this case, which improves the performance. So here how things look like under the hood a little bit. At one end, I have the file path, which is the file path is a name of the file prefixed by the directory path name, where the file is residing, in which directory path. And the other end, you have data blocks, which are stored on the disk in sectors. So you need somehow to map from the file path to the data blocks. And this is what the operating system, file system is a role. Right? You take the file path, which is going to point in some directory structure. You are going to find the file, and the file is going to be you are going to identify by a number. It's called I number. And this I number is going to point to a data structure, which is called inode, which contains all the, the informations about that file, like for permissions, protection permissions, and also information about the blocks or the data in the file is stored. This is the inode. Okay. Here is another view. You remember about this. We had, many lectures ago. This is a view from the process perspective. So here you have a process, you have threads, registers, and you have the address space. And then when you open a file, you get a file descriptors. The file descriptors points to a data structure here, which is in the operating system. It's really at the end of the day, you are going to have the inode. But anyway, the file description here, in this case, you have a file name and you have position. What's the position in the file? What's the position you are going to read and write from? Right, and then you are going, this is going to read from file descriptor 3 and into this buffer, and you are going to copy the data from position 100 in the file. So from position 100 of file identified by descriptor 3, read data into this buffer. But really the way you need to think about this, that instead of this file, you are going to have inumber, like I mentioned. From here, you just need to point directly to this, and inumber points to an inode. But let me ask you this question. Why do you think instead of foo.text here, I should just keep the inumber, right? Which is how an identifier of the operating system of that particular file. Why inumber and not foo text? Let me help you a little bit. Look at this picture. Why inumber and not file.text? I don't want to name my files with random numbers. It's again. You don't name, let me very, very clear here. So from the operating system, from your application perspective, you open a file. And when you open a file, you open foo.text. And back, you don't get a file descriptor. So the file descriptors points to a data structure, which is open file description. This is in the kernel. You see everything which is below this dotted line, it's in the kernel. So, and here when I shown you this example, I will show you that this file is a foo.text, right? Because this is what you opened. But what we are saying here is that we really don't want to keep in the open file descriptor foo.text. Instead, I want to keep the inumber of the foo.text. And the question, why do I want to keep inumber here in this data structure instead of foo.text? File.text is directory independent. Okay, that's a very good point. Let's say it's not foo.text, it's the entire path name. Yes, Jasper. The Jasper, it's correct. Save the first translation step. It's exactly. You see, I open the file and I get the file descriptor. So then I want, if I keep the inumber instead of file path, then I'd save this translation step. Otherwise, whenever I'm going to access a file, I need to do this translation because I have file.text. I need to do the translation to get the inumber. So I save this one, this step. Very good. Okay, let me just go a little bit quicker. So yes, you have a file name, And in a particular directory, so in a particular directory, you are going, the file name is going, you can think about, it's a bunch of entries in this directory. So the file name offset is by going to tell you, the offset is going to tell you what is the entry for my particular file. And then for file number, you are going to have file number offset. Basically, this is what it's I number. The I number, you have an index structure, which is indexed by its of inode. Each entry in this index structure is an inode, which represents all the information associated with that file. And the index in that index structure is the I number. Right, so you have, and the open operation performs this name resolution, basically translating the file name into the file number. And the read and write operations are only referring to the file number, so you avoid the first translation step. And use the file number as the index to locate the inode, and the inode is going to lead you to the blocks. We'll see there a few examples. So you have four components: is a directory, the index structure, is the storage blocks, and free space map. Remember about that. How do you get the file number? You have to look in the directory structure. In the directory structure, I told you that in directory structure, you have entries associated with each file. Each entry, I didn't tell you what each entry contains, but each entry I'm telling you now, each entry, it's a tuple, and which it maps the file name to the file number. Again, when I'm talking about file number, I am also file number is the same like I number, okay? This file number can be a file or another directory, okay? So the operation system stores the mapping in the directory and interprets this format. This tuple, or the mapping between file name and file number, is called directory entry. It's very important to understand, like, again, that the way we manipulate the directory, although in Unix, a directory is just another file, is different, despite the fact that at the lower level, it's, directory is just another file. The way you manipulate the directory is different than the way you manipulate a file, right? You cannot just use the read operation on the file. You need to have special operation, read directory, create directory, or make directory, and so forth. But let me ask you this question: why don't I, again, since at the low level, the directory is just another file, why don't I allow the application to do read and writes on directories? It's dangerous, right? You can override. If you override these mappings, you're messing up, because these mappings are maintained by the operating system, right? It's for the same reason you don't allow the process to arbitrarily modify kernel data structures. That's the reason. This is how the directory looks like. Everyone knows that. So directories are typically organized as trees, directory trees. The leaves in the trees are files. The interior nodes in the trees, including the root, are directories. Okay? And like I said, you do not allow the application to manipulate, to read and write directly on the directories. Instead, to manipulate directories, you have special function calls, system calls, right? make dir or remove dir, create a directory, or read dir to traverse the directory structures. This is from the command line. You can use from the command line, but you also can use them. You have libc support. You can have also use a library. So you can use this programmatically from your application. Link and unlink. This allows you to actually break this hierarchy. And actually you can have a name of a file. You can have a file, a name pointing to an existing file, right? So you have a file with a name, say foo.txt. Now I can have another name called foo1.txt pointing to the same file. We'll learn more about that. So just to give you a sense now, let's assume that about the overhead which are involved. Let's assume that we want to access, to resolve this, to get the I number of the file count, right? And then to access the file count. So what do we need to do here? First of all, we need to locate the root of the directory. We need to start searching from somewhere, from the root of the directory. And the root, how do we do that? Well, fortunately, by convention, the operating system puts the file system, puts the root directory, the root in a fixed position on the disk. So you access this block, data block for root. In the data block, the root, you have this kind of directory entries, file entries in the directory, in the root directory. So you are going to have to locate my, right? How you do that? You can linearly search. Typically, the number of entries in the directory is small. Now, once you locate my, you read the file header for my. Because how do you know that? Because the entry for my tells you what is the file number or for directory my. So from that, you go and read it. Read again the first data block in my, and you search for the book. The third my is going to gain, it's a directory. It's going to keep bunch of directory file entries. You read the header for the book again. You find book, the book entry. The book entry is going to have the file number associated with the book directory. You use that in order to read the header for book, and then you read the first data block for book. You search for count, you find count, and the count is, you get the file number for count, you read the file header for count, and now you are done. So how many accesses? 1, 2, 3, 4, 5, 6, 7. Just to do this resolution. So now you see how important it is to keep in the description of the file, to keep the number, the I number, or the file number, instead of just the file name. Because I save the next time after I open it, the next time when I do a read and write, I save 7 accesses. And accesses are expensive. So, as you know, you also have the notion of current directories, and the current directories, it's if you just refer to the file name without ignoring the past name, you are referring that you assume that in the current directory. The current directory, it's already cached. So it's one way to reduce this number of counts. So this is how happen, the file structure in the memory. And this is a user space, a kernel memory, and it's a secondary storage. This is what happens on the disk. So you have read, when you read a file descriptor, this is a file descriptor paying points into this per process open file table. Each of this entry, it's information associated with that file. And what you are going to get here is a file number and the position, the seek position of the current position in the file. You see this gray thing here? It's again this entry. Let me show you just to connect the dots. Oops. Is this one. The information in that gray area is this open file description, right? The I number and the position in the file. Okay, so this is what is here. So the I number points you to the I node. This is the open file tables, and the I node has protection, bits, and then also has all this, maintains all these data blocks. And all this is maintained also on the disk. The I node information is maintained on the disk because it maintains the association between that file number and the blocks, data blocks, where the data of the file is located. So it must be on the disk. It must be durable because it must persist after you've finish your program, after the program ends. Okay. We talk about all of these things. I'm going to end up with this a few interesting data, and then we are going to continue next time with the file system. So this is a study. It was 14 years ago, but it still is very relevant. And this is, the point here is the following. So what this study is looking over 5 years, and is looking about how the distribution of the file lengths and other information about statistics about the files in a file system. The first important one is basically show you what is the size of the file, the distribution of the file sizes for a file system. And basically what this tells you, this is on the x-axis is the file size and the number of files on the y-axis. So, and this is for different curves, is for different years. So you have something similar, although, as the years pass, you have more and more files, right? And the main point here is this is showing that most of the files are small. Notice that the x-axis is log scale. So these are very small, right? For instance, most of the files are 512 kilobytes or less. There are very few large files. So most of the files are small files. However, if you look at, if I'm taking some piece of data and I'm asking the question from the files, from all the file system, I'm taking a piece of data and I'm asking the question, what is the size of the file which contains this piece of data? Then this is the answer I'm going to get. I'm going to get, and basically you see now that most of the data is contained in big files. So yes, the majority of files is small, but the big files are responsible for most of the data, okay? And I'm going to end up with a question to you. It's a fun question. You see here that on this kind of distribution, you have two peaks. You have a peak around 2 megabytes and another peak around 1 gigabyte, right? So you have, why do you think you have these two peaks? Why do you think this 1 gigabyte? you know, um, what do you think causes it? And by the way, in 2000, it wasn't such a peak, but as the time went on, passed, you have this peak. Yes, let's see. Yes, some very good answers here, right? Yes, video, right? It's like, especially that was peer-to-peer system, maybe you read about it. Yes, this is one reason is media. The other reason is it's a lot bigger and bigger files. These are also binary files. So the executive become bigger over time. But excellent answers. Okay, so with this, we are going to stop here. Again, good luck to the midterm tomorrow, and I'll see you again on Thursday. Thank you.